Okay, so let's look at a few problem types here that you might see. So some problem examples. And we'll be doing tension and plane problems here. Okay? So the first one. All right, so let's look at this example first. If it's going to let me. There we go. Okay. So we're going to put a block on an inclined plane, and we're going to work out how we can sort out its acceleration down the plane if we're not given its weight. Okay, so you sometimes find these problems, and it's actually fairly straightforward to solve, although at first it might seem difficult. Okay, so first things first, we'll try to place this object somewhere on the plane, and we'll come up with a value for the incline. Let's call this 30% incline. Sorry, 30-degree incline, not 30%, 30 degree. And let's draw in our free body diagram arrows here. So we'll have gravity pointing down, right? We'll have our normal force perpendicular. Of course, we're going to draw our vectors tip to tail and make them reasonable in length. Oops. Okay, and then our resultant down the plane is like this. Okay. And so you know from past proofs that we've done that this will also be equal to 30 degrees right here. Okay. So start to add in what these actually stand for. So downwards we have force of gravity, okay, which is going to be equal to mg. Here is your normal force. That is going to be equal to Fg, my hypotenuse, times the cosine of my theta value. And then the resultant force, which points down the plane, is going to be found as Fg times the sine of theta. Okay? All right. So let's say you are asked a problem where it gives you this information and does not give you a mass, no mass given, and it just says find acceleration, and we'll say mu equals 0. So in other words, there's no friction at this time. Okay? So we know from Newton's second law that the net force on this object is going to be equal to its mass times its acceleration. Okay? So the F net on this object is going to be m times a. Okay? So what is the net force if we have no friction? Well, the net overall force is actually just going to be this, right? This is the only force that we're going to be considering in this case. The normal force does not cause the acceleration directly down the plane, nor does Fg. It's the resultant of those two that's causing your acceleration. So essentially what we could then say is we could write this. The net force with this particular setup is going to be equal to Fg times the sine of theta. Okay, so the net force is Fg sine theta. So let's break these into their parts. So F net is mass times acceleration, which we don't know, and Fg is equal to mg. So we've got mg sine theta here. Okay, now if you look, mass appears on both sides, and it turns out that on an inclined plane, all objects, there's no friction, so if we're using balls, for instance, will accelerate down the plane regardless of their mass at the exact same rate. Just like if I drop objects straight down to the ground, they'll accelerate at the same rate. Okay, it's the same kind of principle. The reason why that is, if you want to look at this plane, and then imagine that we take it, okay, and we start to like lift it up, right? We get a higher and a higher and a higher value. As we do that, these vectors also change, right? This is set, obviously. The force of gravity can't get bigger. But as I get higher, right, the normal force, the normal force changes, right? Fg cos theta, as theta gets larger, the normal force gets smaller, right? As theta gets closer to 90, the normal force gets smaller. And then the accelerating force, the Fg sine theta, starts to get bigger. You can kind of see how that would change, like as you moved up, this shrinks and this gets bigger and bigger and bigger and bigger, and vice versa. By the time we get Fg sine 90, well, the sine of 90 should be 1, and the cos of 90 should be 0. So at that point, the downward force is the full force, right? And the object just accelerates towards the Earth. And if we're at 0 degrees, well, sine of 0 is just 0, and then the normal force is equal to Fg when we're flat. Okay, does that make sense? So we're working in between these values, all right? And then what we end up with is just this. A is equal to g sine theta. So you can derive out this formula, and you can always derive it. You don't have to like memorize it, because if you understand the mechanics of this situation, this follows from that. Okay, so mass is not needed in this scenario. Okay, so you can do problems where no mass is given. It's no problem. Mass is given, well, you can go ahead and put them in and solve, but it's irrelevant, right? You don't have to put it in at all. So then the second question probably is, well, what happens if there is friction? So let's redraw it, and let's do it with friction. So we'll make a new inclined plane. Like that. Okay, we'll write in some value. Actually, we'll just call it theta. So we want to write a general formula. Put a ball on there. We'll solve these with numbers later. Let's put a general formula for this. Okay, so now let's say you're given a value mu. If you remember, mu is the coefficient of friction, which essentially is a value that relates the normal force to the frictional force. So I have an object sitting on a surface. I realize that the more mass it has, the higher the Fg will be. And the higher the Fg, the higher the normal force. Okay, and if I'm pushing this object along, we know that that frictional force is going to be related to the normal force, right? So in other words, if I if I have a really heavy object, the frictional force will be larger because the normal force is larger. However, if I lift a little bit, or I place this on an inclined plane, that affects friction. Not because Fg changed, but because the normal force changed. So friction is related directly to the normal force, and it's related through this formula. Sorry, I did that wrong. Like that. So now we're dealing with friction, and let's write that in now. So we still have the same other forces that we're dealing with. So you're going to have your gravitational force pointing down. You're going to have your normal force. We're going to do it tip to tail. You're going to have your FA, your accelerating force, or your applied force, or your resultant force, I should say. And now you're going to have one more thing in the game, and that is frictional force. So friction, of course, always opposes motion, right? Friction always opposes motion. So can we sort out then how we're going to solve for this? So let's just start writing things in. So we've still got Fg, that's mg. We've got mg sine theta down here. We've got mg cos theta here, right? That's your normal force. So just maybe make sure we're aware of that. That's your normal force. Normally it would be up here, but since we're doing a vector diagram, we've got them all tip to tail. And then, of course, we have our last new vector that we're talking about, which is the frictional force. Okay? So frictional force is equal to Fn times mu, or mu Fn, right? So let's just arrange what we're talking about. The F net, the net force in this situation, will be whatever my accelerating force is, plus whatever my frictional force is. Now, be aware, friction is always pointing in the direction opposite to motion. So you have to watch for this, right? In this case, to deal with that mathematically, we're going to have to make it and make sure that it points in the opposite direction. So I'm calling this positive and this negative because I have the power to decide that. It doesn't have to be that left is always negative and right is always positive. That's a convention. In this case, I find when I do these problems, I always want to put FA down in that direction. So let's start filling in what these stand for. So we can have MA here is equal to, right, FA, which is mg sine theta, plus a negative value here, right, which is going to be mu times mg cos theta. Okay? Let's put this in a bracket just to keep its negative in there, right? So what we're saying then is that the overall force acting on this is the sum of FA and FF. All right, so if you look here, we could get M out of everything, right? So the way to think about that is we can just rewrite this like this. Okay, m can go outside of that, right? We've distributed it out, or we've factored it out, I guess. And then if I divide both sides by m goes away. So now I have this, right? I have that the acceleration in a scenario where I have friction just works like this. All right, let's see if we can slightly challenge ourselves here a bit. Let's say you know this. Let's say you know this. Let's say I give you this. Just thinking here, thinking out loud. Let's say that you know the mu value between an object and this plane is like 0.2. Okay? Let's plop something on there so we know what we're talking about. Throw that on there. Oh. My attention to detail bothers me if I don't quite line that up as well as I can. Okay? So let's say mu is 0.2. Now, I'm going to challenge you. What if I ask you this? Calculate the maximum angle this object can stay still, can stay motionless, okay, and not start accelerating. Okay. So again, let's say I have a movable plane here. I can pick this up and lift it up. I realized from past experience that once I get to a certain angle, this is going to break loose and start sliding down. I'm giving you mu. We're ignoring the kinetic versus static friction and just saying it's 0.2. What is that angle? How can I figure that out? For bonus marks, write me a formula for this. Setup. So let's see how we would set up a problem like this. So again, free body diagrams, right? Just start writing things down that you know to be true. Oops, I want an arrow. You know there's gravity. You know there's a normal force. You know there's an FA. And you know now that there's going to be some frictional force, right? Okay. And the frictional force kind of maxes out at a certain point, essentially. Okay? So when you think about it, when you're perfectly flat, right? If this angle was dropped right to the ground, your frictional force would be at its maximum value because your normal force would be at its maximum value when you're flat on the ground, right? As you raise this up, the frictional force will decrease, okay? Because the normal force will decrease. And by the time this gets to 90, right? By the time this gets to 90, my frictional force is dropped to nothing. I can't have a frictional force if I don't have a normal force. Would it make sense, right? I'm just free falling. There just happens to be a wall next to me, but it's not providing friction, right? I have to have some like push into the wall to make friction happen. If I don't have that, I can't have friction. Okay, so then how we're going to lay this out is essentially you kind of have this scenario. When FA is equal to FF, okay, this is the last scenario, the last point before acceleration. So what do I mean by that? Well, I mean this. If, let's say, FA was smaller than the FF, no motion allowed, right? No motion. Can't move. Friction cannot cause motion. So if friction is bigger than FA, there's no motion allowed, right? This is the last point before motion can happen. And then as soon as you get a net force down the plane, in other words, as soon as FA gets larger, motion will start. Okay? So the point we're interested in is the last point possible when we have this. So at what point, what value of theta do we have FA equal to FF? Okay, so that's the logic behind how we're going to solve this. Now we know from experience that FA is found as mg sine theta, and that FF is mu mg cosine theta. So the first thing I want you to notice is that mg appears on both sides now, and therefore it can be eliminated. No mg needed. So now we have this. Okay, and then we have this. Now that's still not solvable. Still can't solve theta. However, this should like ring a bell for people who've taken some math classes. So from math class, from your trigonometric identities, which there's a whole bunch of, but this is one of them, what they will tell you is that the tan of theta is equal to the sine of theta divided by the cosine of theta. Okay, there's a whole bunch of like equalities within trigonometry called identities, and this is one of them. So in other words, we can now do this. Mu is equal to the tan of theta, or better yet, since we want theta, it's equal to the inverse tan of mu. Woo, pretty slick. All right, so there you go. You can now take that and apply it to multiple different types of questions. Hopefully that gives you like a good insight into kind of how a lot of this this stuff works. Some other things that are sort of interesting. You probably remember your like 5 simple machines from the olden days. And so often you'll get pulley questions. So it's interesting just to kind of look at what a pulley is actually doing. So a pulley, as you may or may not know, is essentially just a wheel with a hub that a rope passes over, okay? And if we pull on one side of a pulley, what we'll find is that the pull from the rope is transferred to a different direction, right? So, you know, we might want to move something this way, so we have a scenario where we put a pulley on this end and we can just change the direction of force. Now, a single pulley just changes the direction of tension. There are other setups of pulley that actually give you a mechanical advantage. But before we study the concept of work and energy, we're jumping the gun on that, okay? But basically what they'll do is they'll reduce the amount of applied force necessary here or magnify the amount of force found somewhere else in the pulley system. So I'm talking about things like maybe like a block and tackle where you have this kind of an arrangement, okay? So I apply the force here, and I get 2 times the amount of force here. However, I have to sacrifice how much distance it moves in order to get that, okay? So that's for later. But you will often get pulley questions, and for some reason they baffle people. All you got to understand is that if I pull here and the pulley's arranged like this, that just translates the force into that direction, okay? So that's all a pulley's doing. Now we're going to leave pulleys for a second, and we're going to go to hanging masses again. Okay, so we've studied hanging masses already with angles, but we're going to try a new kind here. So we have this. We have this. Put some ropes in here. And let's put a mass on this guy. And now what we're going to do, whoops, is almost made it. I almost made it without changing the color. This is never, ever going to happen, that I make it through a complete one of these without color change. So now what we're going to say is we have unequal angles here now, okay? So we have one tension here, and we have one tension here. And I guess let's put an F on there so we realize that it's a force of tension, okay? Force of tension. All right. I'll put a mass there. Okay, so I'm just going to do this as generally as possible. So we're going to break this up into its components, all right? So the first thing we need to look at is that there is an FTX over here. called the ft1x, which is going to be equal to ft1 times the cosine of theta. And that, of course, is going to push or pull off to the right. Okay. So again, that's the component of ft1 that's aiming directly right in the x plane. Okay. And now let's lay out its counterpart over here, which is going to say ft2x, x direction, is going to be ft2 times the cosine now of alpha. And that is going to point off to the left. Now, there's no net force on this object, right? It's hanging from the ceiling statically. It's not moving, all right? So the question then is, well, if there's no acceleration left or right, we should be able to say this, right? We should be able to say this. Essentially, ft2 cos alpha, in terms of magnitude, must be exactly equal to ft1 cos of theta. So let's continue on here. So then we also know this, right? We've got fg down, which is equal to mg. And we know then that part of ft1 and part of ft2 are sharing the lift, right? So if I think about that, then I know that I'm going to have to write this really small. ft1 sine theta, well, that's fty, right? That acts in an upward direction. Oh, words are hard today. And then that ft2 sine alpha also shares some of the upward lift. So we could then say this. Fg is counteracted by ft1 sine theta plus ft2 sine alpha. Okay, so in order to solve this, what we're going to have to do is we're going to have to do some of our favorite thing, which is algebra. Okay, so we're going to isolate for ft2 first. We're going to find that that's equal to ft1 cos theta divided by cos alpha. Okay, and we're going to look over here, and wherever we see ft2, we're going to sub in this equation for that. Okay, so now we've got this. Fg equals ft1 sine theta plus ft1 cos theta over cos alpha. Okay. And we also know that Fg is equal to mg, right? Mg equals. And then we can actually like pull ft1 out of there. So we're just algebraing right now. Okay, so then we're going to isolate ft1, which is what we're after. So that's going to give you this mg over sine theta plus cos theta divided by cos alpha. I'm not sure if we can refine that any further, really. Just look here. Can we do anything with this? I don't think so. I think at this point we've got it pulled apart as much as we can. Did I? Yeah, that doesn't look quite right. I did, didn't I? Should have a sine alpha over here. I knew it looked funny. Yeah, thanks. So what I should have over here is a sine alpha as well. Perfect. Okay. There, like that. Oh, sorry, alpha, thanks. Struggling, I can do this. There we go. So let's just rewrite this whole thing right now. Okay. Do a little rewrite here. Okay. So we should have this. Sine theta plus cos theta sine alpha all over cos alpha. Okay. Okay, so now I see something we can do, right? So we've got sine theta over sine alpha over cos alpha, so that can turn into tan alpha, right? So now we can just get to this point. Okay, now I think that's as far as we can go without actually solving it. Okay. So if you were now